Welcome to this explainer. Today, we're diving straight into the invisible magic of how energy actually travels through the world around us. We're going to take some abstract physics and connect it directly to the sounds you hear every single day. If you've been looking for a really solid grade 10 overview of waves, you are absolutely in the right place. We'll be breaking down everything from the simplest transverse pulses right through to longitudinal waves and wrapping up with the incredible physics of sound itself. Okay, let's dive into this. Here's our roadmap for today. We'll be looking at Section 1, Pulses and Superposition, Section 2, Transverse Waves, Section 3, Longitudinal Waves, Section 4, The Physics of Sound, and finally, Section 5, Hearing and Ultrasound. Section 1, Pulses and Superposition, the building blocks. So before we can even talk about a wave, we have to start smaller. We need a pulse. A pulse is simply defined as a single disturbance in a medium. Just imagine you're holding a long piece of string and you give it one quick flick. That single ripple traveling down the string, that's your pulse. And a super important term you need to lock in here is amplitude. Amplitude is the maximum disturbance of a particle from its resting or equilibrium position. Put simply, it's just how incredibly tall that single ripple gets. And this brilliantly illustrates what we call the principle of superposition. Basically, what happens when two pulses literally crash into each other? Well, the rule is surprisingly simple. When two pulses occupy the exact same space at the same time, their resulting amplitude is just the algebraic sum of their individual amplitudes. Think of it like this. If two crests, the high points, overlap, they add together to create one massive pulse. We call that constructive interference. But if a crest meets a trough, a low point, they actually cancel each other out, shrinking the amplitude. That's destructive interference. And the coolest part, right after they meet, they just keep traveling in their original directions like nothing ever happened. Section 2, Transverse Waves, Perpendicular Motion. Now, when you take a continuous succession of those pulses we just talked about, you get a full-blown wave. Specifically, a transverse wave is one where the particles of the medium vibrate at right angles or perpendicular to the direction the wave is actually moving. Think about being in a huge sports stadium and doing the wave. You stand straight up and then you sit back down. That's your perpendicular vibration, right? But the wave itself travels horizontally all the way around the stadium. The absolute highest points of this vibration are your crests, and the lowest points are your troughs. So the crucial point is how we actually measure these waves. And this right here, this is basically your ultimate cheat sheet for your exams. Wavelength, which we represent with the symbol lambda, is just the distance between two successive points in phase, like measuring from one crest exactly to the very next crest. Then we have frequency, which is how many wave pulses happen per second, measured in hertz. Period is the time it takes for just one complete wave to pass by. Notice that formula there, F equals 1 over T. That means frequency and period are exact inverses of each other. And finally, wave speed. To calculate how fast a wave is cruising along, you use the wave equation, V equals F times lambda. Velocity equals frequency times wavelength. Section 3, Longitudinal Waves, Parallel Motion. Let's move on and see how this builds. We just looked at transverse waves, where particles vibrate perpendicular to the motion. But what happens in a longitudinal wave? Well, the particles of the medium vibrate parallel to the direction of motion. This stark fundamental contrast is a huge deal in physics. Definitely keep this in mind for exam prep. Because the particles are vibrating parallel to the motion now, you don't get those classic crests and troughs anymore. Instead, you get regions where the particles are bunched super tightly together. These are high-pressure zones called compressions. And then you get regions where the particles are spread far apart, which are low-pressure zones called rarefactions. Imagine taking a slinky, laying it flat on a table, and just pushing and pulling one end. The clustered, bunched-up coils, those are your compressions. The stretched-out wide coils, those are your rarefactions. Section 4. The Physics of Sound, Experiencing Waves. Have you ever just stopped to think about how amazing your sense of hearing actually is? It's pretty wild that we can instantly hear this massive range of sounds and know exactly where they're coming from. But what is that sound actually doing in the air before it reaches you? Well, take a look at a tuning fork. Sound is, at its core, simply a longitudinal wave created by vibrations. When the metal prongs of that tuning fork vibrate back and forth, they physically smash into the air molecules right next to them. This creates regular variations in pressure. Yep, those exact compressions and rarefactions we just talked about. And those travel outward through the air. Bottom line, no physical vibrations, no sound waves. It's really that simple. So what does this all mean for what we actually hear? It mostly boils down to two main things. First up is pitch. The pitch of a sound, how high or low it sounds to your ear, is determined entirely by the frequency of the wave. A higher frequency literally equals a higher pitch. The second thing is loudness. How loud a sound is depends heavily on the amplitude of the wave. A bigger physical disturbance means a lot more energy, and that translates to a much louder sound hitting your ear. Now, what's really interesting about this is how we can visualize that loudness. Look at a huge stadium crowd blowing vuvuzelas. That is a massive source of intense sound energy. If we capture that sound with a microphone and feed it into an oscilloscope, we can actually see it. But, and this is a big but, pay close attention here. The oscilloscope displays the sound as a transverse wave pattern on its screen. It's graphing the changing pressure over time. So, a really tall wave on that screen means massive amplitude, which means that vuvuzela is incredibly loud. Just remember, the sound itself is still traveling as a longitudinal wave in the air. The screen is just translating those pressure changes into a nice visual graph for us. Section 5. Hearing and ultrasound. Beyond human limits. This is where physics translates directly into biology, right inside your own head. Those longitudinal pressure waves travel through the air and get funneled by your outer ear into the auditory canal. They eventually slam into the tympanic membrane, your eardrum. Because the sound wave is made of high-pressure compressions and low-pressure rarefactions, it physically pushes and pulls on your eardrum, forcing it to vibrate. Then, those vibrations are translated by tiny bones and the cochlea into electrical signals for your brain to process. It is just pure physics at work. But our human ears have hard limits. A healthy human ear can generally only hear frequencies ranging from about 20 Hz up to roughly 20,000 Hz, or 20 kilohertz. Anything vibrating faster than that, sometimes rocketing all the way up to 100 kilohertz, well, that is defined as ultrasound. The waves are there, our biological receivers just can't pick them up. But hey, just because we can't hear ultrasound doesn't mean it isn't incredibly useful. When sound waves hit a boundary, part of the wave bounces back as an echo. Bats and dolphins use these high-frequency ultrasound echoes to navigate and hunt in total darkness. And in the medical field, it's a real game changer because it's incredibly safe. Doctors use the echoes of high-frequency sound waves to create live, real-time images of a baby during pregnancy, entirely avoiding any harmful radiation. And that wraps up our explainer. But I want to leave you with this thought. Knowing that absolutely every sound you hear, from a dog barking down the street to the quiet hum of the computer you're using right now, is just a physical vibration, a longitudinal pressure wave physically pushing through the air. It kind of leaves you wondering, doesn't it? Just how many unseen pressure waves are passing through you right at this exact moment. Keep observing the world around you, guys, because the physics literally never stops. Thanks for joining me today.